Okay, hello everyone, and welcome to today's lecture. I hope you had a nice Thanksgiving holidays. So before the break, we actually had started talking about physical memory um, and from the perspective of operating system. So we had covered how the process isolation is provided by by the operating system by making sure that a process can access only its own address space, only its own address range, and it cannot access the address range or addresses in the within the range of other processes or the operating system, right? So uh, today we will continue the same discussion. Remember last time we started talking about differentiating between two type of addresses, logical address and the physical address. So the logical address is one which is generated by your the program, and and the physical address is actually the actual location on the chip where your data is stored. So these two addresses, they can be same or different, but in the case they can be same in the case where you where a binding of data address or function addresses that is performed at compile time, or it is known in advance. uh, but it is the logical and the physical addresses, they are different in the case where the binding of data and the functions to their memory addresses is performed at runtime or at execution time, right? So if that is the case, which basically mean that if the binding of data and functions to their addresses in memory is performed at runtime, so it's mean that your logical address and the physical address can be different, right? And in such a case, we need some kind of mechanism for translating the logical address into the physical address. So the concept of a logical address space that is bound to a separate physical address space is very crucial in proper memory management. Why? Because if you remember, in last lecture we talked about, like, if we can separate the logical address from the physical address, then it allows the operating system to relocate a process in the memory, which basically mean that we can actually uh, allow a process to be mapped at different locations in memory depending upon the availability of the memory space. So the logical address, it is the one which is generated by the CPU, and it is also referred as virtual address. Physical address is the actual location in the memory chip or the memory unit where we are going to store the data, or from where we are going to retrieve the data. As I said, logical and physical addresses, they are same in the compile time and load time address binding schemes. Uh, why? Because program is in these binding schemes, when we are binding the data and the and functions to their addresses at compile time or at load time, in those schemes, uh, program is not moved around in memory once it has started executions. Since it is not moved around after it has started the execution, it's mean that the address is always fixed once the execution has started, right? So that's why uh, uh, we uh, we can have the logical address and the physical address can be same. However, logical and physical addresses differ only in the execution time address binding schemes. So here is an example to understand how logical and physical addresses they are translated, how logical address is translated into the physical address. This is like a very basic approach, but there are more advanced mechanisms which provide more flexibility. We will we will have a look at them hopefully in today's lecture. I will try to cover it today. If not possible, then in the next lecture. So remember in last lecture we talked about base register and the limit register, right? So what was the purpose of base and limit register? Two. There were two purposes. First, they together allow us to separate the address space of one process from all other processes in an operating system. How? By making sure that all the addresses generated by a all the addresses generated by a process, they are within the range. So basically we are saying, if let's say base is 24 and limit is 32, then we are saying that all the addresses that will be generated during the execution of the current process, they will be in the range of 24, from 24 up to 24 plus 32. So there will be, if any address that is generated outside of this range, that address will be treated as illegal and the memory access will not be allowed. So that is the one purpose. Second purpose is second purpose of using base and limit register is relocation. So like for example, if I simply change base value of the base register from 24 to 10, so the range will be from 10 to 10 to 42. Range of all the addresses that will be generated will be 10 to 42. So and our program, it will be loaded in the memory accordingly, right? Now let's have a look at how. Sorry, my throat is not feeling good. So let's have a look at how logic and physical addresses are translated. How we can translate logical address to the physical address. So let's first have a look at this program. So if let's have a look at just the logical address. So what is the logical address? So logical address is like uh, it is the address range uh, the, which is generated by the program, right? So what is the potential address range? It is the set of all addresses that can be generated using a given length of the address. So for example, if I say that the in once let's say for example, let's say in the microcontroller which you have studied in your assembly language course, that microcontroller uses 8-bit addresses, right? So so let's say if you have 8-bit addresses, so what are the total number of locations which you can use, which you can address? 2 raised to power 8, right? So 2 raised to power 8 means 256 locations. So the address range will be 0 to 255, right? So it's mean that all the addresses which your program can generate, they should be in the range of 0 to 255. So this is the logical address range, right? Similarly, if you have, let's say, a 32-bit address, 32-bit address range, so the total address range will the total address range will be 0 to 2 raised to power 32 minus 1, right? So you can do the math. So the set of all addresses that can be logically generated by a program on a given architecture is known as logical addresses or logical address range, right? So here in this example, the logical addresses are like starting from 0. So here we are assuming that each instruction takes 4 bytes, right? So if each instruction take 4 bytes, then the first instruction is located at address 0, next one is located at address 4, next one is located at address 8. But remember, this is just logical address space, which means that this is how the programmer is viewing the program, right? Programmer is assuming that when the programmer is writing the program, let's say in assembly language, the programmer is assuming that the first instruction will be located at address 0. The second instruction which I'm writing will be loaded are located at the address 4, and the next one at address 8, and so on, right? So we are keeping this example simple where we are assuming that each instruction takes 4 bytes, right? But again, this is the programmer's view of the addresses. These are not the actual addresses in the memory where your data will be stored, right? Now, when this program is compiled and then it is loaded into the memory, and then when the program runs, so within the program, like you have instructions, right? So for example, here you have this instruction, move this one, move RIM28. So basically it is saying that move in the register R1 the data from the memory location at address 28, right? So now let's have a look on the left side where we have the CPU, which is actually running this program. So here this program is only loaded in memory, right? So it is just a file, executable file loaded in the memory, and this is the content of the file, right? And among the in the content of the file, there is an instruction at the logical address 16, which is saying move data from memory location 28 into R1, right? Now let's say that when this process is running, remember from the previous lecture that whenever a process is launched or whenever it is executed, or whenever it starts executing, the base register and the limit register are loaded with its appropriate value. Now let's say if the value of the base register is 24 and the limit is 32, and then these values are loaded into the registers, and that time and the like at the time point where we take the snapshot of the execution, we have program counter equal to 16, which basically mean that the next instruction that will be executed will be this move instruction, and in the instruction register we have this particular code of this particular instruction, right? Now, when this instruction will be executed, it will generate the address, right? So it will generate address what? 28. Now 28 is what? 28 is the logical address, which will be generated, right? But this logical address will not be used to access the actual memory. What will be the actual address or the physical address? That address will be generated by adding base value of the base register into the uh, logical address. So 28 plus 24, which is base. So you get 52, right? So this 52 now points to the location in the memory where your data X is stored. Again, keep in mind that logical address is not something which is real. Not real in the sense that it doesn't indicate or doesn't point to a physical location. It is it is an address which exists only in the from the perspective of the process. It is not the actual physical address in the memory chip. Okay. Any questions? No? Yeah, no question. If I would have been in your place, I would have a lot of questions regarding
I
why we
think it
need.
makes sense. So we have our physical address, which is like the real addresses, and then we assign some portion of that physical address as memory for the process, which is then the logical address that it works off of. Yeah.
That's correct. Let me check. Get my pen. Where is that? Yeah, yeah, that's correct. But you can ask the question that what's the point of having these two different addresses? Yes, I tried to answer that earlier by saying that it gives us the flexibility of loading or relocating a program into different locations. But let me try to provide some more motivation behind having two different addresses, like having logical address and the physical addresses for the same uh, for the same program, right? So
Um, I was gonna
yeah, go
ask, would
ahead.
it help like kind of streamline the memory for the process? Because instead of looking through all the memory, it knows that it only needs to look through its assigned memory, right?
Yeah, that is also true, but let me say something here.
Okay.
Yeah, so let me build on top of the same example or same slide which we have here. So here we have like uh, a process which has the logical addresses ranging from 00 to 28, right? So let's say I have program A, or I'm like saying process A, and it has some instructions, right? So right? I'm using the same address. So the first instruction is at address 00, the next one is at 04, and the last one is uh, at 28, right? Right? Now, let's say that we don't have any differentiation between logical address and the physical address, which basically mean the address generated by a program is the same address which is actually used to access a memory location, right? So, mm, so now let's say that here I have memory, and here I have this instruction, as instruction at address 16, which basically says uh, move M28 into R1. Let me write this instruction here. Move R1 from address M28, right? So basically I'm saying that, okay, uh, so when this process is run on the CPU, sorry. So when this process is run on CPU, so what I'm saying is like, if I don't have this decoupling of logical address and the physical address, both the two are one and same thing. So then I'm saying like uh, in register R1, get the data from memory location M28, right? Which is X, right? So get the value of X. Let's say the value of X is 10, and put it in the register R1, right? When you execute this instruction, right? Now just consider Now just consider another case where consider a case where you simply create a copy of this program, or the copy of this program, and name it uh, as program B, but actually the content is exactly same. So you just renamed your file and compile it, right? So, but the internal content is same. So we are just naming it as something different, but content of the executable file are same. So what you will have exactly same set of instructions, right? So this will generate logical address of 0004 up to 28, and again at address 16 you have the same, you will have the same instruction, move R1 from M R28, not R28, only 28, right? So now when this will be executed on the CPU, right? Let's say if both of them are, let's say, executing, you have two different cores. So I'm just naming it, let's say CPU 0 and CPU 1 are core 0, core 1. So this is running on core 1. So when it executes this instruction, it is also saying read the data from read the data from memory location 28 and load it into 10. So which means that process B is basically the address, the physical addresses where the process A is reading the data, and the physical address from where the process B is reading the data is the same address. But this is not what we want, right? We don't want to allow process B to read from the address range of the process A, and we don't want to let process A read from the address range of process B, right? So that is the problem here, right? If there is no how to say, if there is no distinction between the logical address and the physical address, right? However, now this was the case. In this scenario, we had no difference between logical. The address generated by the process is the same address in the which we use to access a location in the memory chip, right? But now if we introduce the notion of the virtual address, or let's say, sorry, if we differentiate between the logical address and the physical address, then we can introduce, okay, base plus limit register, and this one process will also have its own base and limit register. So for example, for this one, we can say, okay, base is equal to 0, and maximum is, I don't know, maybe let's say 32. And for this, the base is equal to, let's say, 40, and range is equal to 32, right? Now, when process A will execute, its address 28 will be uh, will be translated into the physical address, right? And how it will be translated? So it will be translated to 28 plus 0 is equal to 28. And for process B, the address will be 28 plus 40, which will be 68. Now they will end up having they will end up accessing different locations in the physical memory, in the actual memory, even though they are using the same addresses like address 16 and address 16. This will translate into the physical address 16, but this will translate into the physical address 16 plus 40, which is 56, right? So this is why we need the notion of virtual address and physical address. And one other thing is like both of them, both are processes A and B. If you are differentiating between logical and physical address, processes will think like all of the potential address space is available to me. What does it mean by potential address space? I mean, let's say if you have uh, let's say 32 16-bit address, let's say 16-bit address. So process A will uh, think that all the addresses ranging from 0 to 2 raised to power 16 minus 1 all this address space is available to process A, which means that it is allowed to generate all the addresses within this range. Similarly, process B will also think like all the address space, potential address space is available to it. However, because of because of physical address being different from the logical address, these logical addresses will be translated into a different set of physical addresses, and the logical addresses of process A will be translated into a different set of physical addresses, disjoint set of physical addresses. Any questions?
Yeah,
Okay, someone has
just
it. Yeah,
sorry,
go ahead.
related to the example you were just showing, just to make sure I'm understanding. In the picture you show the memory on the right side, right? And for process B, I'm assuming that memory starts at 40, like you provided, right? Like how you have it in the picture, but instead of X being there, like would process B start at 40 instead of 28? Does that make sense?
Yeah, if you are differentiating, actually, I consider two scenarios. One, where we are saying that we don't have a notion of like we don't differentiate between logical and physical address. Both are one and same. Whatever you have value of logical address, exactly same value is used to access the memory, right? Then in the second scenario, we said that no, logical and physical addresses are different. In that case, I said that yes, we are using the base value of 40 and limit 32, so that's why 16 will be translated to 16 plus 40 equal to 56.
Okay, that makes sense. Thank you.
Yeah. Okay. So we have seen a simple example of translating the logical address into the physical address using base and limit register. But actually, in general, the hardware component which is responsible for doing the translation from logical address to the physical address is named as memory management unit. Now, what are the internals of that memory management units? Maybe they are not as simple as only using base and limit register and then adding base to every value of the base register to every address generated by the process. Maybe they are not as simple, as we will see in like upcoming slides. But any hardware unit that is responsible for translating logical address to the physical is known as memory management unit. So in MMU, the start physical address of the program is loaded into a register called relocation register. Actually, this is the same thing which I have explained to you. So relocation register is also known as it is just another name of the base register, because remember, if I take you this example on the one note here, I use that okay, for base we can use the value of 40. So it's mean that any address which is the address 0, it will be converted to 40. Address 4 will be converted to 44. Address 6 will be converted to 46, and so on, right? But if I change, it's mean that my program will be moved in the, will be loaded, or it will be located in the physical memory starting at address 40, not at address 0, right? Now, if I simply change my base register value of my base register from 40 to 100, then the first address of the process B will be actually in physical memory will be the address 100. The next address will be 104, and the next one will be 106, and so on, right? Which mean that by simply changing the value of the base register, I can relocate my program, or I can redefine the location where my program will be loaded in memory, right? So I can relocate my program when I'm loading it by depending upon what is the value of the base register. And that's why base register is also named as relocation register. So in MMU, the start physical address of the program is loaded into a register called relocation register, which is same as the base register. So the value in the relocation register is added to every logical address to obtain the physical address, as I explained. So the user program deals with the logical addresses. So the program, our program, the addresses generated by our program. For example, let's say you are writing a program in C and you say, okay, X is a pointer of integer type, and in that pointer, I hope you guys know how the pointers work, right? So let's say you are saying that X is a pointer of integer type, and in that pointer variable X, you are loading the address of variable Y, right? Now the address of the variable Y, which you are loading into the pointer X, is actually the logical address. It is not the physical address, right? So when you like, but when actually the access is performed in the actual memory chip, before performing that access, that address of Y is changed into physical address. So the user program deals with logical addresses, not it never sees the real physical address. However, however, if you are like let's say if you are uh, writing program in the kernel mode, which means like you are writing code for your operating system or you are modifying some component in your operating system. So there are functions which you can use to convert the logical addresses into the physical addresses, and then you can like print them or see them what is the physical address. But otherwise, if you don't have kernel level access and you are writing a user level program, all the addresses generated are seen by your program will be logical addresses. So pointer values in a C program are all virtual addresses. Programmer does not see physical addresses. So relocation register with limit register can be used for protection as well, just like I explained, right? Hence, relocation register is also known as base register. Did we cover these slides last time? Why I feel like we covered these slides last time? I
I
don't
don't
think
remember
so.
us discussing any of this.
You don't remember, or you
No,
remember? No,
I
okay.
don't.
Okay. Okay. So, dynamic relocation, how we can dynamically relocate our program using the relocation register. It's exactly same thing which I just said. Like you simply need to put a new value in the relocation register. So, for example, uh, as I said, how the hardware will translate each logical address to a physical address on the fly at runtime. So, for example, if CPU is generating logical address 346. For example, as I said, you have uh, a variable y and you want to load its address in the pointer x. So you need to first get the address of y, right? And which mean that so you need to generate the address. So that but the address that will be generated by your program, it will be by your CPU, it will be your logical address. So now let's say that logical address is 346. That is logical address of your variable y, right? And you want to put it in the pointer variable x. So but if you want to access that address, for example, you want to write data in the in the memory at that address. So what will happen is that first it will be converted to the physical address. How? by adding the value of the relocation register to that logical address. So if let's say the value of the relocation register is 14,000, so it will be added to 346 and it will become then 14,346. So this will be your physical address where you will be actually accessing the data. So programs and CPU, they always use logical addresses, and the value of the relocation register, it is set up by the OS depending upon where the program is loaded. And how the OS know where to load the program depending upon the availability of the memory location, right? A memory space, right? For example, operating system is responsible for managing the memory, so it needs to keep track of like what memory spaces or what memory chunks are already occupied or already allocated to other processes, and which memory spaces or chunks are free, so that if like it finds that okay, let's say the address of this memory location is, I don't know, maybe 100, let's say, right? And this one is, let's say, 400, right? And let's say all of this space is already occupied. Only the space between the range 100 to 400 is 100 to 400 is free are available, right? And your operating system need to load a new process in the memory from the disk. Once we say new process, mean it need to load its executable file from the disk into the memory. So it is already keeping track of like which memory locations are available. Now let's say that the size of that executable is only 100 bytes, right? So what your operating system can do is like it can set the base register or the relocation register equal to 100, right? And since the size of the size of the program or the process is only 100 bytes, so it can also set it equal to 100, right? So it will start from 100 and it will occupy all this space. It is allowed to occupy all this space or produce addresses within this range. So all the addresses which will be generated by the program then will be mapped or translated into this address range. So for example, if it will generate let's say address of 0, so it will be converted to 100 by adding 100 to it. If it generates address of 4, so it will be converted to 104 and so on. So relocation register enables program to be put at any location in main memory, right? So let's say for example, here we said that the base registers are again, relocation and base registers are two different name of same thing. So here we said that OS decides that okay, the 100 to 400 is available and the required size is only 100 bytes, so I can set the base register equal to 100. But let's say in a different scenario, let's say all this was also already occupied and there was a space available starting at address, let's say, I don't know, I'm just making up some number, 600 and 700, right? So then what operating system could do that at the time when it was scheduling the process or when it was launching the process for execution, so it can say base register is equal to 600 and then limit is equal to 100. Okay. So you can see that now the program will have been loaded here, not in this region. Okay. Uh, So when we write a program and we actually want to run it on our machine, so it goes through different steps before we can actually execute on our machine. And those steps are consist of, like, for example, we first write the source program, which is like, let's say, our code in Java or C or any other language. Then we feed that program to compiler or assembler, which generates the object module. Object module is nothing but the machine code of our program, right? And then the machine code is fed to another module, which is known as linker. So the job of the job of the linker is to link together multiple object files. If we need to have multiple objects files, then they are linked together into a single executable file. And then the job of the loader module is to load that executable file from the disk into the memory. And once it is loaded, then it can start executing on the processor. So the source program, uh, it uses symbolic names for functions and variables. So when you are writing the code, for example, if you are saying int x are my function, so what is x? X is basically data, right? So it is some location in the memory, but we don't know the address of that location in the memory. So what we do is that we use symbols for memory location. Similarly, my function is what? My function is actually pointing to a location in memory where you have a block of code, right? But we don't know the address of the memory location where that block of code is located. So we simply identify or refer to that block of code by using function names, right? However, when you compile your code, then depending upon if like absolute addresses are used or not, if it is known in advance that where this program will be loaded, then absolute addresses will be used. Otherwise, what will happen is that your compiler assembler will generate an object code or module which uses the relocatable code. Relocatable code is, if you remember from our previous lecture, so relocatable code is like where, for example, if you are doing the jumps, you don't say that, okay, jump to this particular location, but you specify the jump destination in a way which is relative to the current program counter value. For example, you say, okay, jump two locations forward from the current program counter, or jump 10 locations backward from the current program counter. Now it depends upon your where your program is loaded, and based on that, you can move. Your code becomes relocatable. So, uh, at the linker file, the single file which is generated by the linker. So it uses the runtime logical addresses uh, relative to 0. And if you are using how to say execution remember execution time, but if you're using the execution time binding of the addresses for variables and functions, then your runtime logical addresses will be generated, and those runtime logical addresses will be then during the execution translated to the physical addresses. If you are not using if the runtime binding is not used, like compile time and load time binding is used for addresses, which mean that you know in advance that what absolute addresses will be generated, then there will be no physical addresses, and because you are using the absolute addresses, so there will be no translation from logical address to the physical address because they will be one and same. So here we have a tiny example of linking multiple object codes or object files into a single executable file, and how then the data items or functions and different object modules can refer to each other. Uh, so let's say that you have an object file a.o, which has only 80 bytes in size, uh, or 81 bytes. Uh, and it has, among other things, it has a variable x, and it also makes a call to a function called foo. Then we have another object file. So actually, this object file means that it is generated by one source file. Let's say a.c. So a.c is compiled to generate a.o. Then you have, let's say, another source file, let's say b.c, and you compile it to generate the object file b.o, right? And in this file, you have basically the definition of the function foo, which is called by the code in the object file a.o. And then you also have another source file which is compiled into an object file c.o, where you have the main function. And in this main function, you are saying, okay, move number 7 into X, right? What is X? X is this variable. You can ask like how it happens, like if you have a high level language with a function main, how you can use the assembly language. Actually, it is possible to mix the C and assembly language or a high level language. And I don't know about other languages, but at least you can mix C and assembly language in the same file. So it is possible. Uh, you just need to follow certain syntax rules. So then, when you compile these three files by, for example, running the GCC compiler, you get the three objects file A.O, B.O, C.O, and then you can link them together into a single executable file D.xc, right? So as a result of this command, all these three will be linked together into a single executable file. And now when this executable file will be placed in memory, so it will look like this. So for example, if we look at the main, so here in the main, you are saying in the actual source file, you are saying move 7 into X. But when it is like all the three object files are linked together and load into the memory. So here the X is replaced with 20. Why 20? Because 20 is now address of what? The memory location where you have the X stored, right? And similarly, when the in the object in the code where you are saying call foo, so that is replaced with the actual memory reference 170, which is the at memory location or memory address where your block of code for the foo is located. Okay, so dynamic loading. Remember, in last lecture we said that, or even like way back at the start of the maybe like second or third week of the course, we said that when we have a program is nothing but a file, right? It can be in any form. It can be in the form of your source code, or it can be in the form of object file, or it can be in the form of executable file, depending upon uh, at what time of compilation and at what time of like at what step you are in the compilation process, right? So let's say if it is in the form of executable file, but still it is just a file. It is not an active entity. It is just sitting in your disk, right? And when you want to run it, so you need to first that program is loaded into the memory, and once it is in memory, then it is considered as a process, and then the operating system will maintain the process control block for it, and also maintain all others, and then it will become a candidate for scheduling and so on and so forth, right? So forth, right? So uh, now the issue is like, let's say if you have a program which let's say you have written a program which is uh, let me give you an extreme example, which is like 1 GB in size, right? And when I say 1 gigabyte in size, maybe let's say you have a program where you have the main function or the main file, and then you have a header file where you have defined different functions, and then you are calling those functions, not all of those functions. Let's say in the header file you have defined 100 different functions, and then in the main file you are calling only four of them, right? But together main file and the header file constitute your whole program, right? But when you are running the program, actually in the main you are from the main you are calling only four of those functions out of 100 which are defined in the header file. Now the thing is that if so if let's say that the size of, let me go to the one note because then it is easier for me to write. So let's say you have this main file and you have you have a header file, and in the header file you have, I don't know, some defined some 100 functions, but in the main you are calling only, let's say, function 10 and function, let's say, 4. Now let's say the size of this file is 16 kilobyte, let's say, and size of this file is, let's say, only 1 kilobyte, right? So size of your total program will be 17 kilobyte. Now it's mean that I'm just like, it will not be exactly 17 kilobyte, but I'm trying to keep this thing simple. So let's say the size of the executable file is 17 kilobyte, right? So it is residing in disk, right? It is residing in disk here. So when you want to run this program, what will happen that we need to first move it into the memory, right? That executable file. So how much space it will occupy? It will occupy 17 kilobyte, right? But the actual program, when we are running it, right, it is making a call to the function 10 and function 4. Let's say the size of the function 10 here, let's say first function 4, the size of function 4 is, let's say, only 64 bytes. And the size of function 10 is, let's say, uh, I don't know, maybe 400 bytes, right? So out of like 16 kilobyte, we are actually using the code when we run the program, we are using the code which is 64 byte, 400 byte, but we are load. So here you have loaded all 17 kilobyte, but the actual code that is executed is from this is maybe only 64 byte instructions and 400 byte instructions, right? It's mean that other you are wasting the memory. How much memory you are wasting? Let's say 16 kilobyte minus 1 kilobyte minus 64 bytes minus 400 bytes. So you can do the math. What I mean by wasting, you are occupying the memory to load a code which is never executed, right? Which code is that? The code for function 1, 2, 3, and then 5, 6, 7, 8, 9, and then 11 to 100. But that code is never executed. So it is a wastage of memory, right? So that's why there is another alternative. That is, we don't load the program, the whole 17 kilobyte into the memory initially. And what we do is that we can load only the main program, code for the main program in the memory. And when this main program, uh, how to say, actually executes the code from the executes the code for the function 10 or makes a call for the function 10, at that time point the operating system can find, or it can identify that, okay, the code for function 10 is not loaded, so it can load only the code for function 10, or it can load the code only for function 4. So this is known as dynamic loading. So you load what is needed, you don't load everything. So routine is not loaded until it is called. So for example, the code for function 4 will not be loaded until it is called by the main function. Code for function 10 will not be loaded until it is called by the main function. So this result in better memory space utilization, and unused routine, they are never loaded. This is useful when large amount of code are needed to handle infrequently occurring cases. Okay. So we talked about dynamic loading, dynamic linking. So in linking, what we do is that what is linking? So what? Let me try to explain again what is linking using this example. So linking basically means that you need to resolve the memory references. So what do I mean by resolving the memory references? For example, here in main, you are basically saying move 7 into X, right? So but what is X? So I need to first find out what is X and where it is located. For that, I need to look into the other file, which is that which holds the definition of the integer X, which is a.o. So now I need to link a.o into the I need to link a.o with the c.o. And now if I link it, then I can resolve the reference. Okay, X mean, so here I'm referring to X, and where is X located? X is now located in the memory location X, in memory location 20, right? So now I can say, okay, load the value of 7 into the memory location indicated by the address 20, right? And then when in the a.o, I am executing the call, or I'm making the call foo. So, but I need to first find out, okay, what is foo? For that, I can go to the other file and which holds the definition of the function foo, and then I can find, okay, so I can now link it with the I can link it with my program, right? So there are no now two ways. What are the two ways? The two ways, just like loading, is like when you are loading the data into the uh, into the into the memory, and linking is that which object files you are linking into your executable file. So just like loading, you have two mechanisms. You can have two options. One is static loading, that you load the whole 17 kilobyte of your executable file into the memory at the start. That is static loading. And the dynamic is like, no, you load when you load the code into the memory from the disk only when you need it, right? So similarly, there are two options for linking. So, and linking mean resolving the memory references. Resolving the memory references mean that if I want to access a data, or if I want to execute a function, what is the address of that address or data, right? So, but this resolving those memory references, it takes time, right? So what if I am resolving all the memory addresses, but in my whole code, but some of them are never used because they are, for example, let's say I am resolving the address for a function bar, which is part of my object file, linked in with my main file, but that bar function is never invoked by my main file, right? But I already spent the time in resolving the references for the function bar, right? So this is static linking. In comparison to the static linking, what you can do is that you can do the dynamic linking, where you resolve the addresses, or you link the files only when they are actually invoked, right? So the linking is postponed until the execution time. So small piece of what we do is actually that small piece of code, which is known as stub, we use them to locate the appropriate memory resident library routines. So for example, uh, let me go to the OneNote and explain it, right? So from this example, which I showed you earlier, or which I explained on the OneNote, now you understand what it is meant by dynamic loading. Now let's have a look what it is meant by dynamic linking, right? So let's say you are writing a program in C, and uh, it has some function printf, right? Now this print function, if you remember, you have never defined this function, but you are still able to call this function, right? So where is this function defined? This function is defined in a library named C library, right? So in this library, you have functions like, let's say, printf, or mm, let's say, I don't know. I'm not sure where exit is defined with this one, but let's say, so I don't want to feed you wrong information. Let's say some other functions are also defined in this. There are a lot of functions defined in this library, but let's say I'm just using general name function 1 and function 2, right? So one thing is like static linking is that remember, I'm not talking about loading, I'm talking about linking. So static linking is that you resolve this address uh, in advance. In advance mean that before actually this function is called. And resolving it means that you need to maintain, at high level understanding, you need to maintain a table which tells you that, okay, the printf is located at an address, let's say 0x00f0, blah blah blah, right? And but then Printf is not the only function in your program, right? There can be other functions as well, right? And then you need to, if you are doing the static linking, you need to resolve addresses of all of them, all of those functions. Let's say you are using function A. So what is the address of function A? You need to resolve it. Function B, you need to resolve it, right? What if we don't know whether this function will be called actually during the execution of the program or not? The function is there in our code, but whether the function will be called or not, let's say it is a conditional choice. If some condition happens, function A will be called. If condition never happens, function A will never be called. So if that is the case, so let's say there is for the like majority of the cases the condition let's say the condition never happens and function A is never called, but we have already resolved it by through the static linking. So we have wasted our time, right? And we have like linked another file into our the execute into our executable. Which file? The file which holds the definition of the function A, right? For example, let's say C library, or part of the C library which holds the function definition of the function A. But our program actually never calls function A, right? So it's mean that we are wasting both space and our time which is consumed in linking, right? The other option is that we don't resolve the function until the point where our program actually calls the function printf. If and then at that time point we ask our runtime or the operating system is responsible for translating for resolving the function, for resolving the address, and then giving us a address where the actual definition of the printf is located in the C library or any other library. Let's say the address of the function is located in some other library, right? So what is the address where that definition of the function A is located? So these are two options. One is like we resolve the addresses in advance without caring that whether the functions will be called during the actual execution of the program or not. And the second option is that we delay the resolution of the references or addresses until the point of actual call to those functions. So we resolve only those, just like in dynamic loading, we load only the code which is actually used in our program. Similarly, in dynamic linking, we only link into our program only the code which is actually used. And how it works, that how actually the dynamic linking works. So you have small pieces of code known as stub, which are used to locate the appropriate memory resident library routines. So like stubs are just placeholder. So if in the table which I showed you on the one node, so for example, if you are using the dynamic linking, so instead of like the actual address where the printf function is located, you will have this placeholder. So, and which mean that you don't know in advance what address the printf is defined, right? So, but when the dynamic linking will be performed, that placeholder will be filled with the actual address of the memory location where your printf is defined. So stub will replace itself with the address of the routine and then execute the routine. Also, operating system need to make sure that the routine which we are calling, for example, let's say printf, it is in process memory address space, which means that it is loaded into the address space of the process. If it is not loaded, then operating system will first load and then link. Okay, so we have we have until at this point we have talked about the difference between logical address space and physical address space, why we need to maintain this differentiation. Also, we talked about Also, we talked about different steps during the from the writing the program to actually running the program, which is like compiling a program and then generating the object code and then loading it into the memory and then linking it with other object files and have a final executable file which then is run as a process on your CPU, right? So when you want to run a process or when you want to run a program, so you need to load it into the memory. So when you load into the memory, it's mean you need to allocate the memory for that program, right? But the thing is that we don't have at any given time only one program running in our machine. We have multiple programs. It's mean that we need to allocate the memory to multiple processes, right? So the question is that how we allocate the available memory to those multiple processes. And again, we need to allocate the memory not only to the user level processes, but also to the operating system and the system level processes, right? So how we do that? Because we have multiple processes, we have a user level processes, we have operating system, and we have a single, let's say, physical memory. And we all of them are all of them want to reside into that physical memory. So how we manage it, right? So one way is to answer this question is that how we allocate the memory to multiple processes and the operating system at the same time is known as contiguous allocation. So what we do is that we allocate a contiguous region of physical memory to a process or the operating system, right? So normally the operating system is allocated a contiguous region of the memory at the start or at the end of the memory range, right? It depending upon the operating system, right? But it is first the operating system is allocating a contiguous range, and then whatever of the free memory is available, it is it is then allocated to those processes which want to run and which like multiple user level processes which want to run at the same time. So OS allocates memory and loads the program from executable file into the allocated space. Process control block of these processes then include the start, physical address, and the size, which basically mean the base address and the limit. The value for the base address, base register, and the limit register. So when a process is scheduled for the execution, so the start physical address is loaded into the relocation of the base register, and the limit value is loaded into the limit register. Range is loaded into the limit register of the CPU. 13D1 is broken. Okay, I will fix it after the lecture. So in contiguous allocation, as I said, we partition the main memory into two partition. One is reserved for the operating system, and the remaining is used to hold the user level processes. Again, the relocation register, the base register, and the limit register, they are loaded with the values depending upon where operating system want to load a process in the given in the free memory and what is the size of the process. And also these two registers together are used to protect the user processes from each other. So I think we had seen this slide, but let me go through this quickly. We have seen it in the last lecture, I guess. So how these two registers like limit register and the relocation register together, they are used for protection. So any address which is generated by CPU, any logical address. So what you do is that let me just think about it. Yeah, it is like kind of a little bit different scheme. So what you are doing is that you are checking that if the logical address generated by the CPU is it in within the limit. So let's say the size of limit, what is the value of the limit register? Value of the limit register is basically the size of your program, right? Let's say the size of your program is 100 bytes, right? So all the addresses which are generated should be within the 100 byte, less than 100 byte, right? So if they are all of them are less than 100 or 100 byte, then it's mean that it is a valid address. If not, then it's mean that it is an illegal address. And if they are if the address is legal, then you relocate the address by adding the value of relocation register to the actual logical address, which is converted into the physical address, and then you use it to access the memory. You you have quiz today, right? I think you have quiz today. So let me stop here and we can continue with contiguous allegation topic in the on Thursday, hopefully. Yeah. Okay, go ahead and do your quiz, and I will be available until end of the lecture time.